So welcome back. Looking at the slide number this morning, I saw well, about halfway. And there are only 2 lectures left. So I have to aggressively reduce the number of topics I want to mention. That's why I want to talk about, and that's why I have this sheet of paper here. I want to start by correcting a couple of things that I discussed this morning. So there are 2 questions that came up, and I want to just go over those a little bit. So first of all, for this thing here, the interpretation of this result. So when you take the question was, how do you interpret the graph of AB? And the correct interpretation is the following. The graph of AB is the graph that represents all paths of length 2 formed by one edge from A followed by one edge from B, okay? But you have to realize that AB is not necessarily symmetric, and that was what was pointed out. So it does not mean that the paths are both ways. It's only one way. Okay, so it's really a little confusing, but you have to think about this. Here's an example here where you have this is a path this is a graph. It has only one edge. Sorry, it's actually here. The graph has only one edge from 1 to 2. A graph B, it has only one edge from 2 to 3. And of course, there is an edge from 1 to 3, according to this result here. But there is no edge. You cannot just switch B and A. You know, normally we'd like to say that is there an edge going from of B going from 1 to something, and then so if you go B to A will be a path from 3 to 1, but not from 1 to 3. So it's not symmetric. So you have to keep this in mind. That's the first correction. But when A and B are the same, when you have powers of A, it doesn't matter because the matrix is symmetric. Okay. The second thing that I talked about was, let's see, I have to go to here. I think it's 156. Oh, that was right here. Okay. So Hiroshi Murakami asked this question: if the graph is not connected, the closed centrality has become 0, and I answered that this is for the centrality, for the closeness centrality. If you look at the definition, yes, you have some of these. If you have a graph that's disconnected, at least one of these will become 0, infinity, and therefore you have a 0. The centrality in this case would be 0 for all the nodes, actually. So it's not a very good definition for disconnected graphs. Okay, you are either to consider the graph separately, or you have to do something else. Okay, but for this is because it's based on distances. All right, here this one, the betweenness centrality is based on numbers of paths. So it's not. There's no problem there. You can easily see that disconnectedness doesn't necessarily play a role. In fact, you can remove these 2 here, for example, then of course the betweenness centrality of these 2 will be 0. But so sometimes you will have something that makes sense. You can have still a non-zero number there. Okay. So then, as these 2 things cleared up, now I'm going to go to PageRank. So PageRank is a method that was developed early on to measure the importance of nodes. And it was essentially based on this Markov chain model, really. So here's the main thing we do. If you simply say that if a page points to several other pages, then the weighting should be distributed. So you have some sort of probability within. If you think of a row as representing your neighbors, so you distribute the probability equally. So you divide by 1 over the number of edges. Okay, and then imagine that you have tokens that are doing a random walk in the graph, and they will proceed, they will jump from one node to the next as follows. So you're visiting web pages, and you visit the next page in the following with this sort of probability is here. Delta over n chances of going from one of the n links in the page, and then one minus delta chance to jump to a random page. The delta here is a scalar fixed somewhat arbitrarily to be like 0.90 or 0.85. But let's think of delta equals to 1 just for simplicity, right? So this doesn't, you don't have the second case here. So in that case, it's just 1 over n being the number of edges in at a given node. So you distribute equally the probability of jumping to on any of the neighbors. And then the question is, what is the token after a very long time? It's exactly the question we ask when we have when we looked at the Markov chains. So here is the equation you get. That again, assume for simplicity that delta is equal to 1. Then this is exactly, so this is the rho of t of 1 times the probability of going from t1 to ti, etc. So that's what you get as an equation. And that's very similar to what you had with the eigenvector centrality, except that you have this delta here. That's a different, it adds a little bit of complexity. But what this delta does is simply it avoids the nodes that are totally disconnected, or these are called dangling nodes. So in that case, otherwise you would not get any, so you have to, if there is a node that's totally isolated, it doesn't go anywhere. So you have to give it a chance to jump to a random node among all the others. So that gives you, and now you have also to ask to add the constraint that the sum, these are probabilities in the end, just like for the Markov chain. So you have to add the constraint that the sum has to be equal to 1. So delta is viewed as a damping parameter. So we set it to 0.5, I think in the examples I've seen. And then this is the matrix that you set up by for the probability of transition probability matrix, okay? So Hij is 1 over Ti if there is an edge from I to j. And here's an example. All right, actually it's done here. So there's an example in here, and then you can see from this example how you get this matrix. You can jump from A to B or C, A to actually the opposite. So it's A to B or D, A to B or D, either here or here. Okay, with the same probability, which is a half, and then B can go from A or C or D with a probability 1/3. Therefore, because this is the sum, the row sums are all equal to 1. Okay, so then what you do then is actually simulate the walk. So you have, if I want to, if I have a probability, let's suppose I have a probability. For us, this is a row vector. It's a lot longer a column vector now, because we're talking about exactly the same example as we have seen for Markov chains. So think of a row vector that has probabilities in it. Okay, so now I'm going to have, let's see if I can do that here like that. So it has 1, 2, 3. So you have a scalar here, I have a scalar here, I have a scalar here. So that's the probability of being in node A, probability of being in node B. Oh, actually, there's 4 nodes, I forgot. So this is another one here. Okay, so now if you multiply this column, sorry, this row, it's okay. So if you multiply this row by this matrix, you'll get exactly the probabilities of being in these locations A, B, C, D in the next time. Okay, so you keep repeating this. Take now this is to be your new vector, put it here and multiply and repeat this. It's power iteration. It's exactly the power iteration. Okay, and so, oops, I'm going to go here. That's what we have. This is the PageRank algorithm, which is the power iteration for that matrix. And in fact, it turns out that, oops, again, I'm making that mistake of going. So that now we have to add this delta thing, this thing with delta here. So for here, you select a vector. So there is a vector V that's a vector, what is it, something Z somewhere here. Yeah, I had missed something in this whole thing here. Probably, let's see, yeah, this is fine. This is fine. This is fine. And then finally here. Yeah, so you select the initial vector V, and then you just do this. E is the vector of all ones, that's all. And then you keep repeating this. And then what happens in the end is you get an eigenvector. This is V, by the way, is a row vector here. And then you get an eigenvector of this matrix in here. So that's the iteration that you see at the bottom. Okay, rather straightforward. This is what I was talking about here. That's the matrix G. This is the iteration, the power iteration we're using. Okay, so Z is, that's what I was talking about here. So where E is Z transpose, but Z is typically a vector set to be 1 over n times E. So that you have essentially a matrix that is still has stochastic properties. So let's look at this test here that I had in MATLAB. Oh, I don't have MATLAB. That's okay. See, this is going to be centrality, MATLAB. Okay, so we're going to go with the same here. So here's what I have done. Sorry, I'm going to go to and test centrality. So this is PageRank centrality, PR. Okay, here you go. So the same matrix that we saw this morning, I think one of the two matrices, get the plot, and then let's see, I'm going to do a pause again here. And then let's look at the eigenvalues now of matrix B. Why is that? Let's see here. Okay, it's B. So this is eigenvector. So it does first the eigenvector centrality. Let's ignore that one first. And then I'm doing now the PageRank centrality. That's the matrix. That's the, these are the degrees. And I got this vector Z, which I mentioned in the earlier, and I got del is set to 0.85. And then this is my matrix B. It's exactly the same matrix as this one here. That's the matrix what I call B. I would call it G here, but anyway, it's a B. And now I'm going to do, instead of doing the power method, I'm going to get the eigenvector of the eigenvalues of this matrix. It's a small matrix, who cares? So I'm going to take that and then get the maximum one. And then I will just normalize it. And then I would compare it with what MATLAB gives me. The question I had when I was doing this is what does MATLAB do for this delta? What is Z for MATLAB? It turns out they're exactly the same. I didn't realize that. So let's try it. All right. No, it's called, yes, test me on PageRank. So it takes a little while. Hey, oops. Here we go. That's the graph. And this is a slightly different graph from what I saw this morning. And you can tell from here, these two are going to be more important. Now here are, this is the eigenvector centrality here, the ones obtained by MATLAB here. And then my PageRank centrality, the one by the code I gave you, and then the one from MATLAB, exactly the same. Tiny difference in here. I'm not sure that's significant or not. So that's it for this. Any questions? So page rank centrality. So I'm not sure whether Google still uses this or not. I know it used to be a very important problem. We have discovered a new algorithm problem that like has billions of unknowns, and you know, the only way you could solve this in a sort of reasonable manner is to use the power method, simply because anything else would be way too expensive. And it turns out that it converges reasonably fast. In fact, the power method converges reasonably fast for this problem. But now they're probably doing much more sophisticated things anyway. But there's another viewpoint, which is this essentially hubs and authorities. This uses essentially kind of a different viewpoint, but it's very similar in spirit. Okay, so this uses A and A transpose, as you can see here. Okay. Anyway, let's skip that. Now I'm going to go and talk about Laplacians. So graph Laplacians have have a lot of applications that are very important in machine learning. So they tend to be viewed as generalizations of Laplacians that you see in PDEs. So it's a Laplace type. A graph Laplacian is a Laplace type matrix that is associated with indirected graphs. So with an indirected graph. So here is the definition here. If you're given a graph G, okay, and you also given a matrix of weights. So for each edge you have a weight, Wij, and you assume that Wij is non-negative, and Wii is 0. There's no, so it's 0 for II. And it's also symmetric, the matrix is symmetric. And then you build the diagonal matrix D, which is given by the sum of Wij. So Di is the sum of Wij's for I different for all of the i's, because Wii is 0 anyway. So it's the row sum of row I, okay? And then the graph Laplacian is simply this matrix in here, D minus W. So that's the graph Laplacian that's associated with A. And you can think of the simplest case. What is the simplest case? The simplest case is when the Wij's are all equal to 1 or 0. So it's the incidence matrix in that case, right? So that's the simplest case. Then this would be the incidence matrix with the, and this would be the matrix of the degrees, right? It's the sum of the Wij. So you have the matrix of degrees. So the degree matrix minus the incidence matrix will be a typical example. There's one example here. So that's actually where this example I'm talking about here. And here's an example of a little graph and this associated matrix right here. So you can, for example, let's look at row 5. This is the last row here. All right. This one, you can see that you have a degree of 3. So the diagonal entry is 3, and then you have -1 for each entry, for each edge that goes to the nodes 2, 4, and 3. Now this is a little remark about graph Laplacians. How do you compare them with the actual Laplacians? You know, it turns out that the actual for these Laplacians, when you have directly boundary conditions, they don't quite match because you don't have row sum. The row sum is not equal to 0. They tend to be non-singular, whereas the graph Laplacian is singular. You know that because the row sum is the same and is equal to 0. So the matrix times the vector of all ones gives you a 0 vector. So here is an interesting proposition. So L, the graph Laplacian L, is symmetric, semi-positive, definite. Okay. It is singular with 1, the vector of all ones, as an eigenvector, as a null vector. If G is connected, so if you have no disconnection in the graph, then the null space of L is just the span of 1. So it's only one-dimensional, obviously, and it's going to be the span of the vector 1. So if G has K connected components, G1, G2, Gk, right? Then the nullity of L is K, so the dimension of the null space is K. And the null space of L is spanned by the eigenvectors Zj that are defined here. This is actually like a characteristic kind of, these are characteristic vectors, you can think of them that way. So the Zj for component I of Zj is 1 if I belongs to Gj, the component Gj, at 0 otherwise. Really a simple definition. So actually, this is very, it sounds complicated, but it's very simple result. It really is. It shows you also the interaction between graphs and linear algebra. You see, these are eigenvalues talking about. These are multiplicities, linear algebra, and there are very strong connections to graphs. This is connected components. You can count the number of connected components by looking at the multiplicity of the eigenvector, or of the eigenvalue 0, sorry. Okay, so this is a proof is, as you can see here, is actually quite straightforward. Nothing really complicated about it. There is another important definition, which is the definition of oriented incidence matrix. So you define the matrix H. First, you orient the edges. So you orient the edges either I to J or J to I, or you have to give an orientation. Okay, and then the rows of H indexed by so you take now a matrix H, which is such that the rows of this matrix correspond to the vertices, okay, of G, and the columns will correspond to the edges. So it's a matrix that has number of columns is the number of vertices, the number of edges, the number of rows is the number of edges. And so you essentially, you put, for each ij, you define, let's forget the scaling first, you put a 1 in I and -1 in j if the edge goes from I to j. And then you scale that so that you have by the square root here of wij. So if wij is 1, this doesn't matter. So here's the example I showed earlier. This one, 5. This one is 5. So you see how you have exactly 5 vertices, but you have 4 edges, 1, 2, 3, 4, and you can see easily that this is the H matrix associated with it. This is the first edge. It goes from 1 to 2. That's 1 from 1 to 2, right, etc. Okay, so here's the property that's associated with this. It turns out that the graph Laplacian is equal to H times H transpose. So you can. This is not useless. It's actually important for some to prove results. For example, you can immediately see from here that the matrix has to be symmetric positive definite, right? Semi-positive definite. You cannot say that H is no singular, is full rank, but you can see immediately that it's SP semi-positive definite, at least. Okay. So now let's go through a few properties of graph Laplacians. So there's a strong relation between this, what I call essentially Rayleigh quotient. When X is norm 1, this is a Rayleigh quotient associated with L and X, and the local distances of the entries of X. So here is the result. So let L be any matrix so that you have this basis. Suppose you're taking just the graph Laplacian. Okay. Then X transpose Lx is half of the Wij. It's the sum of the Wij xi minus xj squared. Okay, so it really is very simple result. It shows that this Rayleigh quotient is essentially half of this sort of quadratic form in this that makes the distances between points in the vector come out as an important quantity. So you have this could be useful in some situations. I'm going to see that in a second. Then you could generalize that, which is actually the more important result. You could generalize that to vectors. So instead now of having a vector here, you have this would be a block of size. It has to be something like this, right? So that you'd have something that's consistent here. So this is, I should probably have taken the transpose here as opposed to, this is because the notation that is in some literature uses this. So the matrix Y is flat and thin, okay? So this is equal to the sum of Wij's times the differences between the norms of the columns of Y. That's why actually one of the reasons why you use this as opposed to the other one. So if you take the distances between the columns of Y, the distances squared, add them up and multiply them by Wij, then you will find exactly this trace here. Okay. So this is a particular case where you have this matrix which has some importance. It's a covariance matrix. Okay. All right. Property 6, which is useful for graph partitioning. Consider the situation where Wij is either 1 or 0. If X is a vector of signs now, let's suppose X is a vector of +1 or -1 entries. Then X transpose Lx, according to this result here, the difference here is either, well, because Xi and Xj are either 0, either -1 or 1, this has to be either 0 or 2, right? So you take the square and you immediately see that this is 4 times, it's 4 comes from the squaring of 2, times the number of cases where you have I and j that are, Xi and Xj that are different, and that means it's an edge cut. You're cutting the edge. Yeah. So if you take two nodes here that are on the same side, Xi minus Xj would be 0. So it doesn't come in your account. If they're on this side, it's 0. But if one of them is here and the other one is here, then Xi minus Xj would become 2. And then you square that and you get 4 in the end. That's exactly this result here. Okay, that's useful for graph partitioning. Okay, so then the question is, how do I use this? I would like to minimize the number of edge cuts, number of times that Lxx essentially is not, the number of times that Xi minus Xj is non-zero. Okay, and then subject to the fact that I also want to have about the same number of nodes in the first set and the second set, and that is expressed by this relation here. E is the vector of all ones. So if I say E transpose X equals to 0, I am imposing the fact that you have as many -1s as you have +1s. So instead of solving this problem, this is whenever you have a combinatorial problem like this, where you have a +1 and -1, and that becomes a hard problem to solve. It's combinatorial, it's messy. But what you usually solve is a relaxed problem, a relaxed version, meaning that you change the -1 and 1 into any variable, and you just take the signs of this thing. So you replace X by any vector, and let's do that here. So instead of solving that problem, now I'm going to solve this. So this is the result. First of all, let me remind you of some of these results. I'm sure you know this. So the minimum of AXX divided by AX. So the minimum of the Rayleigh quotient is the smallest eigenvalue. And if you take the minimum of AXX with a condition that X is orthogonal to the first eigenvector, then you get the second eigenvalue. So what we're going to do is solve this problem here, because we have to, this X orthogonal to U1. U1 is what? In the case of Laplacian, the graph Laplacian, U1 is the vector of all ones. We know that. The eigenvalue, the minimum eigenvalue is 0, right? So the U1 lambda 1 is 0, and U1 is the vector of all ones. And this condition here just can be expressed by saying that E transpose times the vector U that I'm looking for has to be equal to 0, because it's the vector of all ones is orthogonal to the vector X, and this is U1. So that's the same condition as saying E transpose times X is equal to 0. So that's what we solve. We're going to solve. So instead of solving this, we're solving this. This is the relaxed form of the problem. And what we do is then take, instead of taking X, because we need plus 1 or minus 1s, you just take the sign of the vectors. Plus or, if it's positive, you think it's a plus 1. If it's negative, you associate the minus 1. Or to be more, a little more precise, you actually take the median. It's a little better. So the sign of the median will give you the assignment of plus or minus 1. So this is what recursive spectral partitioning does. You take a certain domain, you partition it in two with the first eigenvector the first time, and then you cut pieces as you go. So you take this one and cut it in two, and then the largest one you cut in two, etc. So you take every time you take the largest partition and cut it in two. Okay. So these are some of the approaches taken for graph partitioning. Spectral is usually combined with some sort of coarsening to get a small graph. Then there are geometric techniques. These are not really that much used anymore, but they have some theory. And then multi-level, you combine with spectral, etc. Okay, so I'm going to show you a little demo here. Graph partitioning, all right. And I have two, as you can see here, I have two tests. I'm going to show them both. So first of all, G partitioning, okay. Let's say the first one here, test by this bisection simple. Okay, so what this does is actually it would be too long to explain what it does. It's a small semicircle. You do a finite element assembly. You get a matrix, and then you look at the eigenvalues, and now we get the field vector. The second vector that is associated with the lambda eigenvalue lambda 2 is called the Fiedler vector. That's the one you use for partitioning. And then you just look at what they did exactly with the median, and then the largest is the positive would be would be assigned to one set and the negative to the other set, and you stop there. And then at the end, I show the plot. So again, a lot of details skipped, but the main ideas are just that you generate a mesh, and then you use this graph partitioning exactly as described in the notes. So test this here. See if that works. Here we go. That's the original graph. So this is just there's no partitioning yet. This is just the original graph. It's a half circle, a half disk. And I generate that by a very, very simple set of commands. You can see that in the notes later in the MATLAB scripts that I attached to the notes. And there's a little bit of an assembly done, and then you get that. So now let's look at the second figure. I hope it's behind this. All right, so here it is. This goes away. And look at this. It separates that almost exactly in half. This is on one eigenvector only. Okay, it's only one eigenvector. And you get two sets in here. Okay, right. So now I could repeat the process by taking this set and cutting it in two, etc. But instead of doing that, I will show you an example with the one that I test mesh partitioning. Right, this is a real mesh, and we're going to do. I think I have four domains. Here's the mesh here, and this is in the domain in the CFD literature, this is an example that's well known. It's called the NACA 11 mesh. And so you just read the data, and then you pass that as a graph, and you partition it in two, and you can guess which one was the first partitioning here. It's actually, this is the direction. Let me just see. Oops, sorry about that. I didn't even do this. Oh, I thought I was doing, yeah, so it's actually this side in here. This is probably the first partitioning, right? It's smooth. And then you took this one, cut it in two, and then you took this set and cut it in two. And you could ask for 6 if you want, you get the same. Let's see if I can do that here. Let's see, I think it's in test mesh. Right, now I give the number of domain, it's called ND. ND is the number of partitions. 4. So let's see, I could have just set it there. 6, okay, let's try it. I'm gonna, for 6 domains. It didn't seem to do much. Oh, it has because it's there. And D is equal to 6. Right again. Right, now we got 6 things in here. The reason why it didn't work before is because I had it in the wrong place. They changed it, they have to change it. So this is now, what happened is the ones that were cut, I'm not sure exactly which ones. This one here probably cut, etc. Okay, and you can see that there is a lot of stuff going on in this region here. Okay, good enough for this. Any questions so far? Okay. So this is another approach. I just want to skip that part. So now we'll talk a little bit about clustering. So I think, remember what the problem is. We have set of data, and you would like to get exactly the same thing with partitioning, but now it's no longer simply a graph, but it's data. When you have data, you want to partition it somehow. That's essentially what clustering does. So there's a simple example in here where you have materials and you want to partition them in groups, okay? And then these are digits, you want to partition them in groups. This is another example. Okay. So what is unsupervised learning? Unsupervised learning is a class of methods that do things like these. You have data and you would like to extract some information from the data. For example, how do they cluster, etc. Okay. That's one of the most important examples is that of partitioning. So this is an example we did with Jay way back, right? A few years back. Jay is here. Is on using essentially techniques from sparse matrix computations to do some sort of clustering. So you take a matrix that totally. This is an example from actually from the elections in. Was it? Yeah, I think it was about just prior to some elections. I forgot which year it was. And then you look at the discussion blogs, of the discussions between people, and you're trying to figure out how you can cluster them. And it turns out you can just look at techniques based on blocking for sparse matrices, getting a block structure, and you can get very easily something like this. And so it's an interesting illustration of some technique that's used for sparse matrices that was turned out to be useful in a different context. So there are some references here and things like that. Okay. So there's a basic method which is used everywhere, and that's a k-means. So I'm going to just say a few words about k-means. So this is a method for clustering. You have data, and you would like to find clusters of the data, and with each cluster you associate a center, which is the centroid of the data. So initially you select those p centroids somewhat arbitrarily. Okay, actually it's not entirely arbitrary, but let's suppose you select them totally arbitrarily. And for each point, you determine the centroid that's closest to it. Okay, and then you assign that point to that class, the centroid. See, that belongs to this cluster, the cluster related to the centroid that's closest to it. Now you do this for every node. Now you have clustered, you have a set of subsets, okay, each associated with a centroid. And now you do the opposite thing. For each subset, you compute the centroid of that subset, okay? And then now you have a new set of centroids. You repeat the process that I just described, the two steps I've just described, and you continue doing that until things stabilize. That's really a simple technique, right? It's a greedy algorithm. So the next thing I will discuss is methods based on similarity graphs. So in order to be able to do many of the things we do in this context, we need to associate a graph with data. So you call that a similarity graph. You have data, and when you associate with it a graph. Okay. So let me just show. Here's the picture that I was mentioning here. So you have I. The goal is to build a similarity graph between I and some points. Okay, so actually I don't know what these points are, the neighbors, but I want to say, let's suppose I decide that I have some neighboring nodes here, and I would like to assign a weight for each edge from each of these edges. So I want to build a similarity graph, a graph that captures the similarities between two items. Okay, so the simplest thing you can do is use a k-nearest neighbor graphs. So you have points here, and you define a proximity measure, for example, some distance, okay? And then you want for each point, you want a list of the nearest neighbors to that point. Okay. So here's the data, and this is the graph you want. Question is, if for example, I want just k of these neighbors for a given node I. Okay, so we'll revisit this issue here. There's a whole sort of set of methods to find k-nearest neighbor graphs. But for now, I just want to mention two things that are very commonly used. One is called the epsilon graph, and the one is the k-NN graph I just mentioned. So in the epsilon graph, you say that xi and xj are connected if the distance between xi and xj is less than a certain epsilon. Okay. The k-NN graph takes as k nearest neighbors. So you take a point and you take the k is a number, like for example, 10 nearest neighbors of graph. So k-NN graphs are directed, right? Epsilon graphs are indirected. So this is a good property, but they're complicated, and you don't have to choose the epsilon. So there's advantages and disadvantages to both of these. The one thing that's commonly used is for weights is to define. This is actually something that's used in things like segmentation and so on. So here you have some scalar here which defines, it's like a characteristic, some measure of similarity. You can think of this as just a constant equal to 1, for example, in the simplest case. And then you have these distances squared, the negative, and you take the exponential. And you only consider some of them because otherwise you get a dense matrix. Okay, only consider the nearby points. So then this thing is actually used, or see in a second how they're used for things like segmentation. Okay. So now let's look at generalization. I talked about graph partitioning. Now we're going to look at this generalization of this notion when you consider data. So we have data. It's just, for example, matrix of data items. And from there, you can get KNN, nearest neighbor graph, or some similarity graph. And now you're ready to do something like this. Right? You say, how do I partition this graph? So you have you got it from data to a graph, which you want to partition somehow. So you build the graph Laplacian first, and then you will partition the set V into two sets, A and B, such that this is the partitioning, all right? And the definition, you got cut of AB is the sum of W of U and V. So W is the weight that you have here. And so this is the number, what we called this edge cuts earlier. It's no longer edge cuts, it's something where you have a weight associated with each edge cut. So that the idea is to try to minimize this, right? You try to minimize the edge cuts or the cut of AB. So, but if you did that, you'd end up with a situation like this, for example. This would be, it would have a very small cut, right? But it's terrible as a partitioning, as a clustering. You would rather have something like this in the middle, right? This one, the line that you see here. So that's how the people devised all sorts of mechanisms to avoid this problem. And one of them is ratio cuts. So you try to minimize the cut subject to dimension. This is what ideally you would like to do. But the actual approach in practice is just to minimize the cut of AB divided by the product of the cardinalities. This is difficult to find a solution to this problem. There's a lot of work. And then the actual one, this is some results about theoretical results, etc. There's some nice theoretical results, but the practical aspects are not very interesting. The one that is more interesting and is used it was used a lot in the past is the Shi-Malik normalized cuts approach. And what this does is simply use this definition. So you have the cut of AB divided by W of AV. So this is the number of, so the sum of the Wij's when I belongs to A and J belongs to V. To all, V is the whole thing. And the same thing here, you do the same thing for B. So it's some sort of volume of exchange or something like that between A and V, and then B and V. And to make a story short, this is a long one. It actually gets a little messy, but in the end, the result is very simple. The result is you need to solve an eigenvalue problem like this. So it's a generalized eigenvalue problem where D is the diagonal of this Laplacian, the graph Laplacian, and N is just a Laplacian. So this is, it goes through a lot of stuff to reach to this point here. Okay. So this is just some properties here. And then you can extend that to more than one cluster, to two clusters. And then I will show you how this is used. This is actually the Shi-Malik approach was quite popular in segmentation. What is segmentation? You have an image that you would like to find parts of. For example, let's see, I can see here a group, that's part of the auditorium, and then this part in here, and then so these things would be clustered into different pieces. If I have a tool that could do that, sometimes it's very useful. You could separate the person from the background. You could separate. There are a lot of uses of this thing. For example, so now let's go back here, and I'm going to show you a demo with the segmentation. Okay. Okay, so what I have here is just two tests. I think there's one test. This is a very simple one, which is mirror. And I think, oops, why is it that I don't have MATLAB here? Oh, I exited MATLAB, okay. Okay, so test mirror, I'm going to show you what it does. All right, so it generates a picture. So actually from the same group that Jim Nagy was mentioning yesterday from Denmark. They have this tool, the toolbox, and they had this little for regularization. That you generate this image very simply with, it's actually a few lines of MATLAB code. And then you ask the question, can I find what these pieces are? Okay, so you ask the tool to, I think this is done with, I'm not sure it's done with k-means or, yeah, I think it's done properly with k-means. And he finds these 3 pieces without a problem. You know, actually 4 pieces because there's a background here. So you give it 4 and it finds them automatically. Okay, so in fact, show you mirror. This is the image. And then I say actually 3, my k-means. Okay, and then I use my k-means I did myself, and then I did the, so how come it is 3 and not 4? Let's see if I can say 4. Is that 4 or 3? You get it from the same color? Okay, let's look at that. Let's try it again, run it here. Yeah, now we said exactly those 4 images, but before I had, so you had green, yellow, this light blue and dark blue. But if I say 3, if I say 4, 3, what happens? It should give me 1 that's the same as the other 2, but I don't think I saw that earlier. Ah. All right, so let's try it again. This is with 3. Well, yeah, exactly. I found these 2 are the same. So you cannot, you know, if you give it something that's arbitrary, you cannot find those. And then you find 1, 1, 2, and 3. Let's take the other example now. This is actually an image of a man jumping. No, this is, yeah, this one here. This is the image. And then I try to segment it by k-means using 2 domains, and it finds this. Very, very simple. Okay, good enough. Any questions? So segmentation was one thing. This is actually a general approach for spectral clustering. So, see how am I doing here? A few minutes left, my goodness. Yeah, so this is a general approach, okay? You're given data. So this could be an array of size, this is like D by N. N is the number of samples, number of items you have in your data. And from there, you build a similarity graph, which is this thing here, okay? And then typically you compute a few of the smallest eigenvalues and eigenvectors of the graph Laplacian. So the smallest eigenvectors, k of them, not 1 or 2, but k of them. K is some number you decide. And then what you do with this, you use k-means to cluster these eigenvectors. And that gives you a fairly powerful technique, okay? That the reasoning behind this is what we saw earlier for this problem when we talked about the eigenvectors. You know, remember the example, the result we saw, which says that if you have k-connected components in a graph, the Laplacian will give you essentially a null space of k, in this case 3, and these eigenvectors are formed this way, have like 0 values here and non-zero values here, etc. So if you compute the eigenvectors, if it's not exactly separable like this, then if you cluster these, you'll find exactly these. If you cluster the approximate eigenvectors, then you find exactly this perfect clustering that you see here. That's the motivation for this. Okay, So now I'm going to start skipping. This one, I will just tell you about the technique that was we developed 2 years ago again with Jay Chen, who is here, on how to build the KNN a graph, right? How do you build the nearest neighbor graph? So you have data and you want to get the graph like this. How do you do that? Well, we use this idea of divisive partitioning, developed actually by a colleague at the department, Bully. And what you do, you have your data. You first of all you scale it and shift it. You shift it so that it has zero mean, and then you can split x hat in two halves using hyperplanes. Then using the SVD simply of this largest singular vector, not the SVD, but the largest singular vector. Here's how it works. If your data is here, this is an intuition that you get from mechanics, right? If you then the hyperplane that separates this thing in two is actually U is the one that's the principal axis. U is the principal axis, and the orthogonal to it will be hyperplane that will separate this in two. So what we do is simply take that eigenvector, and every VI that's positive is one set, and VI that's negative is the other set. And then you repeat the process recursively on the subsets. Okay, that partitions the graph, and at the end you build the KNN graph in each node. This is cheaper, and then you're all set. You're going to have to glue these things together, and I'm going to skip that part because it's a little too long. Okay, now graph embeddings. So I am still at page 216, and I have 100 pages to go. What I will do tomorrow is go directly to just a couple of topics. So today, I think we're almost at the end here. There's 2 minutes left. So I'll just maybe briefly talk about the graph embeddings. These are methods that were developed in the old days to essentially do the opposite of what we just did. In the what we have done so far is have data and you get a graph from it. Now consider the opposite problem. You have a graph and you want to work with the graph with vectors, things that we know how to handle, right? We know how to deal with vectors. And so you want to get the representation of the graph with numbers. So you have a graph and you want to get data from it, sort of representation. For each node, you have a vector that represents it. For example, I mentioned that application earlier where you have a graph and you actually it's the opposite thing where you have a data and you want to graph. You have a graph and you want to get coordinates representation in 2D so that you can view it. That's the example I showed you at the very beginning with Markov chains. So I'm going to show that tomorrow. You'll see that you can do something that's not as good as the one that's done by MATLAB. I don't know what they use. I have to look into what they do exactly to get that mapping. So graph embedding is essentially a way of getting data representation, vector representation for graphs. And so let's see this tomorrow. I'm just talk about just a couple of topics selected from what's left. And I'm going to answer questions you might have here. So I have there's some things in here. Questions. If the graph partitioning can be made uniquely and geometrically invariant under the change of numbering vertices, then the graph isomorphism problem could not be hard. Oh, so this is a question from the same person, Hiroshi Murakami. Hello. If the graph partitioning can be made uniquely and geometrically invariant, yes. Then the change of numbering vertices under the change, okay. Invariant under the change of numbering the vertices, yes. Then the graph isomorphism could not be that hard. It's actually, you could do something like this, but you don't get, the graph isomorphism is really a hard problem. You cannot solve it in all situations, but you can get an approximate solution by doing some things like this. You can take the eigenvectors and, in some situations, it's actually not too bad. So there's some special situations that gram isomorphism not too bad. But if you try to think of solving the general problem, then it's much harder. So I think things like this could be useful in some situations, but I don't think they resolve the whole problem. Otherwise, we would know. Any questions here? Let's see if there are anything else. All right, and then I think we'll adjourn again for today. I'll see you tomorrow. Thank you.